Now in this video we are going to look at the photoelectric effect, that is investigating the stopping potential. In the first video we looked at an introduction, that is what is a photon, the photoelectric effect, we looked at work function, and also looked at kinetic energy, the photoelectric equation, that is HF is equal to HF naught plus half mv squared. Now we want to investigate the stopping voltage. We have this experiment here which consists of an adjustable PD, microammeter, and then we have collector, which is the anode, and emitter, which is the cathode, and then we have a voltmeter that is across the whole thing to measure the PD. Now at first this must be negative on the left hand side, this must be positive. Negative so that it becomes the cathode, and then positive here so that it becomes the anode. So electrons are emitted from the cathode and then they get attracted to the anode. So the incident light, remember we said that the incident light must have frequency enough to knock off electrons from the surface of the metal here. So if we use very weak, like if the frequency is very low, then nothing will be emitted from the surface. The frequency is high, even for a very low intensity, we're going to get electrons being emitted from the surface and then suddenly attracted to the collector. And this whole thing must be evacuated so that the electrons do not bump into air molecules that will be present in there. Right, so I said that at first this is negative. Now we start adjusting the anode so that it becomes more negative. That's what you're now seeing there. It's now being made negative. So as you're adjusting it becomes more negative, such that the electrons that are emitted from the surface they are repelled off by this collector, so that we have very little electrons reaching there, and then keep on adjusting until, so how do you know? You know through this microammeter. So you start having the current decreasing on the microammeter, very small current, and then you adjust, keep on adjusting until you've got zero deflection or zero showing there on the microammeter. That means that those electrons with the maximum kinetic energy have been stopped. We then read off the PD that is displayed on the voltmeter. That is called the stopping voltage or the stopping potential. So photoelectrons travel from the emitter, that is the cathode, which is the metal surface, to the collector, the anode, when radiation falls on it. The frequency of the incident radiation may be varied using color filters. Making the collector more negative with respect to the emitter by adjusting the PD decreases the number of photoelectrons reaching it. When the current becomes zero, electrons with maximum kinetic energy fail to reach the collector. So the stopping potential is the negative potential applied to the collector to stop electrons reaching it. Or you could say the positive potential applied to the emitter to stop the emission of the electrons. So it's either way. So you could make this more positive such that you do not start having less electrons emitted from there, or you end up having nothing emitted from there and you don't get anything recorded on the microammeter. So the kinetic energy of the electrons is transferred to electric potential energy as the electrons approach the collector. So the loss in the kinetic energy is equal to the gain in the potential energy. Loss in Ke equals charge of electron times potential difference, that is QV. Remember, electric potential energy is given by QV. So the work done or gain in potential energy of an electron is EVS. Remember, in place of Q we are now putting E because these are electrons. So EV, and then this is electrons with the maximum kinetic energy to be stopped. The potential read off is the stopping voltage. So EVS is equal to half mv squared maximum. So remember from my previous video, HF is equal to work function plus half mv squared maximum. Work function is HF naught. You remember that. So it's going to be that. And then HF is equal to W plus EVS. So we are substituting the maximum kinetic energy by the EVS. Rearranging the formula, you're going to end up with Vs is equal to H over E F minus W over E. Now we can plot a graph of Vs, the stopping voltage, against frequency. So it means your gradient is going to be H over E and the y-intercept is going to be minus W over E. Now if you plot the graph quite well, you're going to get a straight line that is that which has the intercept, y-intercept right there. There's going to be an x-intercept again here where the graph crosses the x-axis. That value is the threshold frequency. So the threshold frequency depends on the material. It's a property of the material. Different materials have different threshold frequencies, hence different work functions. Remember, work function also is dependent on the threshold frequency. Work function is equal to hf naught. So we're going to get different y-intercepts for different metals. So for different metals, you see the other two graphs there, you then establish their different threshold frequencies. The stopping potential is the same for a beam of low intensity and for one of high intensity. Increasing the intensity just produces more photoelectrons, but it does not affect the graph in any way. Now let's look at an example taken from June 1997. Electromagnetic radiation is incident normally on the metal surface of a metal. Electrons are emitted from the surface and these are attracted to a positively charged electrode as shown. The current recorded on the microammeter is 2.1 microamps. Calculate the number of electrons emitted per second from the surface. Now let's study this a while. So this being connected to the positive, it becomes your anode, and then this one becomes your cathode. So which means that electromagnetic radiation comes in, photons knock off electrons, and then they are suddenly attracted to the positive there, and then the circuit is complete, and then you register something there on the microammeter. This is evacuated, like I said, so that there is no disturbance in the movement of the electrons that are emitted from the surface by air molecules. Now it says calculate the number of electrons emitted per second from the surface. We know the formula Q is equal to IT. Now we're saying the time is 1 second because it's per second. So Q is equal to IT. I is 2.1 times 10 to the power of minus 6. So we're going to get the number of electrons. Then you divide that charge by the elementary charge, 1.6 times 10 to the power of minus 19. So 2.1 times 10 to the power of minus 6 divided by 1.6 times 10 to the power of minus 19. B, the incident radiation is wavelength 240 nanometers. Calculate the energy of a photon incident on the surface. E is equal to hc over lambda. H is 6.63 times 10 to the power of minus 34. C is 3 times 10 to the power of 8 divided by the lambda shown there. Remember, these are nanometers multiplied by 10 to the power of minus 9 meters. Part C, the intensity of the incident radiation is 8.2 times 10 to the power of 3 watts per square meter. The area of the surface is 2.0 square centimeters. Calculate the power of the radiation incident on the surface. Remember, intensity is equal to power over area. So to get the power, you say intensity times that area. It's going to be that value that you're seeing there, 8.2 times 10 to the power of 3 times this 2.0 times 10 to the power of minus 4 square meters, converting these to square meters. 2, the number of photons incident per second on the surface. Now we know that power is equal to energy per second. So energy per second. So what we got there in C1 is the energy per second. So we want to find the number of photons incident per second on the surface. So you've got to divide by the energy of one photon that you got there on B. Right. So just let me know in the comments what value you get. If you get the values that are written there, then that's fine. So this should be energy that you got here, energy per second, divided by energy of a photon. Then hence determine the ratio number of electrons emitted per second over the number of photons incident per second. So you're now saying the number of electrons emitted per second is what you calculated in part A, and then you divide that by the number of photons that you got here in C2. So part A divided by C2, you should be able to get that value, 6.5 times 10 to the power of minus 6. Then says comment on your answer to C3. So what it means here is the number of electrons that are emitted is way less than the number of photons that were incident. So it means less photoelectrons were emitted from the surface as compared to the photons that were incident. So a fraction, only a fraction of electrons were emitted. So about 1 in 1.5 times 10 to the power 5 photons incident on the metal surface releases a photoelectron. I'm going to reserve wave particle duality for my last video, and in this video I'm also going to look at electron diffraction in line emission spectra. Signing out.